So last session we were talking about liquid penetrant inspection, and we walked through the process of applying penetrant, allowing it to dwell, then removing excess penetrant, whether it's rinsing it or wiping off with a solvent damp rag. And we did also talk about post-emulsifiable, the process that involves post-emulsifiable penetrants. However, we're not going to do that in lab. And then the last part of that was then you have to apply a developer and allow it to develop, allow it to sit again for a period of time before you try to view or search for any discontinuities or cracks, because we have to pull that dye back out of any cracks and crevices. This inspection portion, this goes back to kind of one of the disadvantages of this method. Is that it's basically a detailed visual inspection. So you're going to be looking for those indications, and you can be, aided by, you can use different devices to aid you in this process, magnifying glasses, flashlights, mirrors, etc. I have flashlight for type 2, but we actually now have flashlights for type 1 as well. We have the black light flashlights that you can use. But just some things to know while you're doing your inspection is, if you're doing a type 1 inspection, you're doing it under black light, we got to be careful about the amount of white light that's out there, the amount of just ambient light. So when you're in the lab, when you're doing this in the NDT room, we can close the door and we have black lights in the room and all that. But if you're working, in the hangar, if you're doing portable liquid penetrant, you have to work in a hangar environment or out in the field, you may have to come up with a way to shield yourself from white light. And one way we did this at the airlines was to simply take a heavy black trash bag and kind of cut it to make a little tent out of it and just tent it over ourselves while we're performing the inspection portion. We do all the application and the dwells and all that just under the regular white bright hanger lights, and then for the actual inspection we kind of tent ourselves in, just kind of put it over your shoulders, the back of your head, and the part, and create like a little tent to be able to block out that white light. If you're doing type 2, you want to make sure that you have sufficient white light, type 2 again being color contrast. You want to make sure that you have sufficient white light to be able to see what it is you're looking for. If you're in a dim environment where there's shadows being cast on it, it can hide or make it hard to see that. So this inspection it's going back to that detailed visual inspection, some of the different techniques we talked about with detailed visual inspection. But the downside is that it is prone, there is a certain amount of human error that can come into play when you're doing this. So you just got to keep that in mind. A little bit more information about black light. We talked about this in mag particle, but again, a reminder is we're looking at ultraviolet light right at the edge of visible and ultraviolet spectrum. So the ultraviolet light is going to, for type 1, it's going to excite the fluorescent dye and cause it to glow. And so our black light, just like with magnetic particle, we're going to use the same black lights that are in that 3500 to 3800 angstrom or 350 to 380 nanometer wavelength. And the optimum wavelength for fluorescent penetrant, just like mag particle, is 3650 angstroms or 365 nanometers. And so our black lights, whether they're a halogen black light or LED black light, they're going to put out light that's kind of in that range. It'll put out a certain amount of ultraviolet light, it'll put out a certain amount of visible light because it's right in that range, and then there's going to be a purple filter. So you can see here light, the fifth one down. Light is a 100-watt mercury vapor bulb with a purple filter. So that's the old school, is the mercury vapor bulbs. But then using a purple filter lens to really filter that down so it's as close to just the 3650 angstrom light as possible, or the 365 nanometer wavelength light. A key with this is that, and this applies to magnetic particle as well, is that you have to have a minimum strength of light. So you have to show that you had enough light for the penetrant to glow effectively. And so that measurement is, we have to have a minimum of 1,000 microwatts per square centimeter at 15 inches. And so what we do is we get a device called a radiometer, which is a light meter. And radiometers, different radiometers can be calibrated for different light ranges. And so there's visible light radiometers. Think about what photographers might use to judge, photographers or cinematographers, movie makers might use to judge light in a scene. Or the one we would use here is for these black lights, is we would have one that's tuned to that 3,650 angstrom range. And so you would point your light at it, you'd put your light 15 inches away. It has roughly a 1 centimeter square or square centimeter opening that the light hits, and it's going to make sure that you have at least 1,000 microwatts hitting that spot. These actually can be used both ways. So most people have gone to what you get now is a dual radiometer, one that has a black light sensor and a white light sensor. And so what that can show is it can measure and show that you have that minimum 1,000 microwatts per centimeter squared at 15 inches of black light. And then it also tests the white light to make sure your ambient white light isn't too bright, and just proves that you're in a dark enough space that you'll be able to see things properly. As I mentioned back, we have some of these older mercury vapor bulbs in our lab. They're actually getting very hard to find as they've burned out. I've gotten them, replaced them, but I don't know how much longer I'll be doing that because they really aren't making them very much anymore. But the industry is moving almost exclusively to LED black light sources, and they can be, they're different. They come in different sizes. They can be very small all the way up to big. They are more compact for the same strength, the same wattage. And probably one of the biggest advantages is that they don't put out heat like the mercury vapor bulbs do. And as such, they can be shut off and turned back on at will, versus the mercury vapor bulbs used in the older lamps. When they get hot, if you shut them off, you have to wait for them to cool back down again before you turn them back on, or you'll heat shock them and crack the bulb or ruin the bulb. So you're seeing black light sources across the industry, and we got a couple of those flashlights just so you can use them. Again, just pointing out where this falls. So, visible light is the range we can see there, from about 400 to 700 nanometers. And black light is just below that. It's technically a form of ultraviolet light, but it's not considered particularly dangerous to the human eye. Whereas if you were to use ultraviolet light that wasn't filtered and it was coming in at the 150, 200 nanometer range, that's getting into the stuff that the sun gives off, the ultraviolet that you wear sunscreen to protect yourself from, and can wear sunglasses to prevent from damaging eyes and skin and that kind of thing. As part of the liquid penetrant process, one of the things we have to do is verify that our system, and by system I mean the equipment, the chemicals, and the process you follow, is performing as it should. And so what we have is something called a Tam panel, and this shows a Tam panel that's been processed. You're all going to get the opportunity to do this. We have one of these Tam panels in the lab. It's one of the items on your lab projects. And what you do is you use whatever process it is you're doing on this Tam panel, and on one side of it, it's rectangular, and one side of it is polished, and then has five it's almost like it's been shot with a BB. It's got 5 pip marks in it, and so these 5 pip marks, when they're on here and they're shown across the bottom, that's what the arrow's pointing at here. So there's one. They correspond to the 5 different levels of type 1 penetrance. So that would be a 1/2. This one's for a 1, a 2, a 3, and then on this panel you can't see it, but there's another pit mark right here, and they have the cracks get smaller. The cracks that were caused by each of these pit marks get smaller as you move, in this case from left to right. And so if your penetrant process, if you're using a level 2 penetrant like we have in the lab, a level 2 penetrant, you should be able to see the first 3, a minimum of the first 3. So again, half, 1, and 2 should all show up if you're using a level 2 penetrant, and if you've done the process correctly. If you're using a level 4 or 5, or sorry, 3 or 4 penetrant, then you'll get these other dots. Now, sometimes even with a level 2 penetrant like we have, it's not unheard of. If you've done it carefully, you've done it properly, even with a level 2 penetrant, you may get a indication at the level 3 point like we have here. But it just needs to have a minimum. It needs to show a minimum of a level 2, or it has to have a minimum of whatever level it is you're working with. The other thing you'll notice here is there's kind of a division. We've got the top half and the bottom half here. The bottom half, the areas that don't have penetrant in them, so around the flaws, that is the polished area. So you should be able to rinse off just about all the penetrant that's on that polished area. It shouldn't really stick. And then above the line I drew there, that part that's glowing, that is rough. That's a rough surface. And the idea there is, you can see in this case it's glowing, and it should maintain a certain amount of penetrant. And so what that tells you is, when you're done, if you have a bunch of extra glowing area in the bottom half, so if I get my highlighter and you got a bunch of dye kind of glowing in an area, that means you underwashed. You didn't clean the Tam panel well enough, and you left residual dye there. If, on the other hand, the upper half doesn't have this nice kind of consistent coating of glowing penetrant on it, the rough half, but if you've washed it to the point where that doesn't glow at all, then you've actually overwashed the panel, and it means your wash process was too aggressive, and you could have potentially washed dye out of cracks and crevices, that kind of thing. So it allows you to check both your chemicals, your process, and how it all comes together in order to perform these checks. Another kind of just reminder, we've talked about this with some of our other methods, but our flaw category, our indication types. So remember, a real or relevant indication is a true flaw. So if we go back to our Tam panel, in this case, the various flaws, the pip marks across the bottom, the 4 glowing kind of circles or stars here, those would be relevant indications if this was a part. And then non-relevant is result from a known cause, such as surface finish, forging marks, etc. And that's to be expected. So in theory, on here, we're looking to get this glow on the top half of this panel. But if this was a part, say a rough cast part like a connecting rod, this area in the top half that's maintaining dye, that would be on a part that you're testing, that would be a non-relevant indication. And then finally, remember the last one, a false indication is something caused by a process error or a lack thereof. So, things like insufficient wash. So if you did this and you had a bunch of dye on the bottom half of this, not on the pit marks, but just on the surface, that would be a false indication caused by underwash, by not cleaning enough of that excess dye off. At the same time, if you looked at this and there were areas on the top half that were bare of dye, where on the rough half, the top half that should have dye, if it was bare, that is actually an indication that you overwashed the part, and so that would be a false indication as well. And so then you can have other things like dwell time being short or long, thumb or fingerprint. If you leave fingerprints on a part, this one here, you can kind of make out they've got a piece of wire or something tied in the hole at the top here, and that's to be able to hold it without having to put fingerprints on it. With ours, we don't have anything in that hole, but you can handle it by the edges. Most parts you want to handle by the edges are areas that you're not looking for some kind of a flaw to prevent or to minimize any instance of false indication. So that wraps up liquid penetrant.